Thank you.
Thanks, guys. So here we go. As I said, I'm Jonathan. I work at CoreOS based in Berlin. And I just want to give a quick shout out to the container game people because they made the speakers all these great little marshmallows with our avatars on them. So I'm really, really happy to have one of my bear. Okay, so today I'm going to talk about Rocket and Kubernetes and how these things fit together. So first, just to start off, pretty briefly, go into what is Rocket? What makes it special, or what kind of characterizes it? So Rocket is an app container runtime, and it's an app container runtime for running apps on Linux with a few different kind of focuses. We talk a lot about sort of security, composability, and standards. First, to kind of focus on what an app container is, because in the talk before lunch, Mark talked a bit about these differences between sort of app containers, system containers, and the sort of stuff that Snappy's moving into. For the purposes of Rocket and Kubernetes, an app container is a pod, and this is sort of this fundamental execution unit. So it's the smallest unit of execution you're going to consider when you're running in a containerized environment. But what that actually comes down to is a grouping of one or more applications. So maybe you're grouping a web server and a little backup daemon, or a little service discovery thing alongside your database, or anything like that. Rocket pods are pretty much synonymous with Kubernetes pods in terms of the technical definition and also sort of the theoretical definition. Quick history of Rocket. Project's about a year and a half old. When we first announced it in 2014, it was very much kind of prototype, just trying to drive this conversation around these things in the container ecosystem that we thought were kind of lacking and not really being discussed enough. Because we think competition is healthy, we're big believers in open source, and that we think it's better to have multiple competing tools to sort of drive innovation in the ecosystem. Fast forward a couple of years, or a year and a half, and we got to Rocket 1.0 earlier this year, and since then we've been really, really active. We've actually had 14 releases in the last 6 months or so, and so the latest release came out, I think, last week, Rocket 1.14, with tons of new features over the last six months. As I said, one of the focuses is security. What this means to us sort of, philosophically, there's kind of two aspects. One is from the UX perspective, we want things to be secure by default. So we want, your standard experience of running a container, an app container with Rocket, to have as many sort of security features enabled by default as possible without having to sort of opt in. What we think security should be more of a sort of opt-out thing. So basic things that, at the time that we sort of started designing Rocket that were really lacking from most common sort of container use cases, things like verifying images, verifying the integrity of the contents, and then restricting the capabilities to sort of the bare minimum of what's actually running. And then the second side of Rocket security is the architecture and the way that we integrate it with other things. And I'll talk about that more in sort of the composability side of things. But essentially it means that what Rocket does should be well-defined. It should be well-scoped. It shouldn't try to do things, it shouldn't try to do everything. So very specifically, it won't try to do things like, container orchestration. That's what we have Kubernetes for, or other systems for. And we should provide clear integration points so that we can hook Rocket into these different systems. Another part of the sort of the Unix philosophy, classic Unix philosophy, is you might have different operations that you want one system to be able to do. You can do with different sort of privileges. So for example, if you're just fetching a container image over the internet, you don't really need root, right? You just need to make some HTTP calls, pull stuff down to disk, and maybe extract it. You don't need to be a long-lived root process to do all that stuff. On the other hand, if you're starting up a container, maybe spinning up a VM or doing a chroot or things like that, and in a modern Linux system, you still, for most intents and purposes, you still need root privileges or something very close to root privileges, like capsysadmin, for example, to do these things. But that doesn't mean we need to grant those privileges to all operations. So that's what we mean by sort of the Unix philosophy. In terms of the actual technologies involved, pretty much we try to take advantage of everything that Linux offers. Rocket is very focused on the Linux kernel. So some Linux-specific things like namespaces, different namespaces, more newer namespaces like user namespaces to allow you to separate the users in the container from what's running on the host. Things like SE Linux contests to isolate pods on the system from each other and also from the host. We have one of the sort of more special features of Rocket is this support for a VM containment. So it can use a backend, which I'll talk about in a minute, that actually gives you full hardware CPU supported isolation. And then we have this other feature called sort of TPM measurement, which allows you to get this cryptographic record of everything that's running on your system from the boot time up until when your application containers are running. And again, these are some of the things that we've added in the last few months. More fine-grained Linux capabilities, so you can tell your container, while you're starting it up, exactly what it should and shouldn't be able to do, just to more tightly restrict the sort of attack vectors. We've enabled setcomp by default, and again, restricting the interface between the applications and the kernel, because in a containerized environment, typically what the containers definitely share is the kernel on the system. So you want to make sure that they're only doing what they absolutely need to do with that kernel. So there's less chance of them sort of escaping that or affecting other applications. And we've also put in some work to mask getting sort of sensitive paths to applications. But the real point here, or the takeaway here, should be that security is never something that we see as complete or finished. Certainly with this fast-moving sort of ecosystem and fast-moving technologies. So every month or so, there's either a new feature or there's some really important bug fixes in the Linux kernel for a lot of these technologies. And for us, it's always an iterative process. Part of the reason we are working so quickly on Rocket and doing releases so regularly is so that we can take advantage of these things and these bug fixes as soon as possible. And that sort of flows through from all of sort of the CoreOS approach to software. So again, the next aspect that we try to focus on with Rocket is composability, making it composable, making it integrate well with other systems. And there's two sides to that. One is the external composability, which is using Rocket as a tool and integrating that with your init system or with an orchestration system like Kubernetes. And the other is internal composability. And that comes back to the different backends that I talked about earlier, allowing us to use different container technologies under the hood without users necessarily noticing. So they can get advantage of more secure containers without it affecting their end user experience. So again, focusing on external composability, a big part of that is this process model that I talked about earlier, where Rocket process is a Unix process, and that means that anything you do to that process from your system's perspective applies to the whole pod. I'll dive into what that looks like in a second. The sort of corollary to that, is that there's no long-running daemon that monitors Rocket pods or anything like that. They're all self-contained processes, but we do have a daemon that you can use to explore information about pods, and we're using that pretty heavily in the Kubernetes integration. And then finally, this idea of pod level and app level properties. So I talked about how pods are grouping of applications. Well, you might want to apply certain containment primitives, like memory constraints, to a pod, to everything in that pod. But you also might want to have more granular control and be able to control things at the app level as well. So here's our pod. It's pretty simple. It's just got two applications in it. As I said, a pod is sort of a grouping of applications in a shared context. And here, this is sort of a bit of an abstract context at the moment. What this looks like in terms of Rocket and the sort of staged architecture I talk about is we have three stages. We have 0, 1, and 2. And 0 is the UX, so that's the Rocket command itself. So that's what you run on the command line or your integration system runs. And then that sets up things to invoke stage 1. And the way it invokes stage 1 is it actually calls an exec on stage 1, which means it totally replaces the Rocket process. So after Rocket's pulled down the images, extracted them to disk, set up everything ready to go, it gets out of the way, and then it's gone. It's replaced entirely with what manages stage 1, which is your pod. And then within stage 1, you have the actual apps, the actual code that your developers write and deploy in container images and want to deploy on Kubernetes or Docker Swarm. And those are what we call stage 2. And the stage 2, what we have there is we have a contract between the stages. So we know that stage 2, something running in stage 2 can always expect to see, its file system, its app container image. It can always expect to see a shared network that it shares with the other apps in the pod, these kinds of things. So I mentioned that Rocket actually just calls exec, which means it gets out of the way. So this is sort of conceptually what's going on. After Rocket actually invokes stage 1, it kind of gets out of the way entirely. So in terms of getting back to more something like a process tree, you have, Rocket doesn't stand alone on the system. You have something invoking it, whether it's someone on a command line running bash, or it's your init system, probably systemd, or it's the kubelet in the Kubernetes world. That's going to start the Rocket process, using the standard kind of Linux way of doing a fork exec typically. And then Rocket's going to just exec the stage 1 right over the top of itself. So you actually have the stage 1 process as the child process of whatever's invoked it. And then your stage 2, the actual applications, are children of that encapsulating stage 1. What this means is that if we run, our run command is something like systemd run, which if you're not familiar with systemd, what this basically does is starts up a command line, starts up a sort of a transient unit in systemd. So it starts up the command that you give it, everything from here on, with a set of parameters that systemd provides. So for example, a memory limit parameter, and then it runs it off in the background. It's the equivalent, if you're used to Docker, it's the equivalent of doing like a Docker run -d, except systemd is then looking after it on the system. So what this gets us, first is we get this pod level constraint. So this is a 1 gig memory constraint that applies to the entire pod. Nothing in the pod, the overhead of these two applications in aggregate can't exceed one gigabyte. It'll be limited that way. But if we sort of move further along in our run command here, and we're actually giving to Rocket this time, we're telling it, oh, we want to limit the memory to 512 megabytes for this particular app 1, then what we get from what Rocket provides is an app level constraint of 512 megabytes. So in this example, maybe we want the pod, these two things together to only ever use at most 1 gig on the system. But within that, we can be a little more granular and say, well, I don't really care how much memory this one uses, but I never want this process to use more than 512 megabytes. So that's what we get when we talk about these different app level and pod level properties that the Rocket sort of architecture provides. The other side of composability, so that was sort of the external composability, what people using Rocket and what systems using Rocket can control. Internal composability is the staged architecture I sort of mentioned, where Rocket, the command line, and the API is just like the UX, the API, but the actual underlying technology is just an implementation detail. So a user shouldn't need to care about that. So we have these different stage ones based around these different technologies that provide different features. So the standard one, which is based around systemd nspawn, is very similar to a Docker container, an LXC container, a runC container, that it just uses the sort of classic Linux technologies of cgroups and namespaces to constrain a process. Where it gets a bit more interesting is we have a what's called an LKVM backend, and so that actually fires up a very, very lightweight virtual machine. The guys at Intel working on something called the Clear Containers project put a lot of effort in to make this very, very efficient, very fast, so it spins up in milliseconds rather than seconds. And then actually, that's soon going to be deprecated in favor of new work that they've been doing around QEMU, so actually putting QEMU, the sort of hypervisor, in as a backend. I mean, again, they've done a lot of efficiency work to make that just as fast as spinning up a container. So coming back to our sort of architecture diagram here, again, we had sort of whatever the invoking process is, starting Rocket, which basically launches the stage 1 over the top of itself, and the stage 1 is what encapsulates the pod. What that actually is in the default setup is an nspawn process. So systemd nspawn, which is responsible for setting up all the cgroups, setting up the isolation at that pod level and that sort of thing, and then maintaining the processes within there. But because we have this staged architecture, we can change that stage 1 to be a KVM, an LKVM process, and from the outside, things look exactly the same, and from the inside, things look exactly the same. So the apps, shouldn't notice any difference, and the end user or the kubelet or systemd shouldn't notice any difference, because the contract, the API, is kind of provided between stage 0 and the process. Or similarly, as I said, you assume we're going to be moving to QEMU, so that's going to be able to swap that one in instead. We also have a special kind of stage 1 called Fly, which is really more about an unconstrained environment. There are certain things you might want to run. You might want to have the advantages of using a container tool, but around the packaging stuff, so being able to discover and pull down images from the internet securely and manage them that way. But you might actually need so many advanced kind of requirements, like the kubelet would be one example, where it needs to do things on the host, and it doesn't actually need any isolation. It just wants to have its image file system that runs there, but be able to do pretty intrusive stuff on the host. And we have a special kind of stage 1 for that called Fly, which is not really a pod. It's just sort of a single process running on the system. And then the final part of Rocket I want to talk about pretty briefly is sort of standards and compatibility. So when we started Rocket, we had attempted to do the sort of first well-defined attempt at the app container spec, of what a container is. And the motivation for that was, we want different people to be able to build tools around containers and being able to integrate containers and write, tooling to work with different container tools in a single way we can kind of agree on, so we don't need to just buy into one particular ecosystem. AppC, I'll sort of talk about what that got to in a minute. Then the second part of the thing that came out of the Rocket project was CNI, which you might have heard of, the Container Networking Interface. And this is just pretty simple, basic, common networking plugins, kind of plumbing that you can use with all these different tools like Kubernetes, Cloud Foundry, Calico, Weave, to set up network interfaces for a Linux container. Docker can run Rocket can run Docker images natively. It's been able to do from almost the beginning and up to the latest sort of Docker formats. That's actually what we need to do in Kubernetes for reasons I'll get to in a second. And then finally, there's a bunch of standardization stuff still kind of going on, and we're very, very active in these fields. So to talk about that very briefly, as I said, AppC started as like, hey, we want to define what a container image is. We want to define what like a pod is. We saw some adoption of AppC, but there was some notable kind of entities in the container space absent from this effort. And so rather than pursuing that, we ended up sort of coming together to form this new organization, OCI, the Open Container Initiative. And the intent of that is that will sort of deprecate and subsume a lot of the stuff that's happened in AppC. A lot of the things we were pushing, like image signing and distribution, and some of these well-defined like format of what a container is, so anyone can build a container image and like know that anything compliant with that will work. That's all happening in OCI now, and we're very, very close to sort of a stable format there. And then finally, CNCF is another newish foundation as well around sort of harmonizing cloud native technologies. So this is now the parent foundation for the Kubernetes project you might have heard of. And we're also seeing some discussion there around other aspects of sort of standardizing things like networking and stuff in the container space. Okay, so that was Rocket in a nutshell. Now Kubernetes, very briefly. Kubernetes is a cluster-level container orchestration system. You've probably heard of it. It handles all this cool stuff that you want from an orchestration system, like being able to schedule containers in a cluster, being able to upgrade them on the fly, recovering from different failure modes, being able to scale things automatically, magically, all that great stuff. The Kubernetes architecture at a very, very high basic level, you have sort of what we call the control plane, which is a lot of the kind of interesting business logic, like this is where you're going to schedule things in the system. This is how you interact with Kubernetes, because that's where the API is hosted. This is where your replication controllers and all these primitives in Kubernetes that do all the business logic live. And then you have a much larger kind of pool of nodes, which is basically they're a bit dumber, like they're just like the worker kubelets. They just sort of do what's given to them. So they receive jobs or they receive pods, and then they run them on the system. So again, Kubernetes is often talked about as container orchestration, but really what it is it's not specific to Docker containers. It's the API. When we look at how we interact with Kubernetes and the sort of primitives that it defines, it always talks about it in terms of pods. So there's no need for it to be strictly coupled with Docker containers, and we think we can do some interesting work by pushing that pod primitive kind of lower into the system. Again, pod is sort of grouping of one or more applications. Talked about that a bit earlier. And again, the Kubernetes definition is very, very similar to, or basically synonymous with the Rocket definition of a pod. So how does Kubernetes actually contain applications? Well, as I mentioned, kubelet's the thing that runs on all of the systems in the cluster, all of the worker nodes in the cluster. And it basically gets pods assigned to it, scheduled by the control plane that we talked about, and then it runs them. And how does it run them? Well, it just delegates every part of that running a pod to the container runtime that's sitting on the node as well. So the kubelet, talks to the container runtime somehow. This is, Docker, for example, and it'll say things like, I want to start a container, I want to, fetch this container image, I want to kill this container, all these kinds of things. The way this is actually implemented is that, deep inside the kubelet code, hundreds and hundreds of lines of code, there's this thing called the Runtime Interface, which is a Go interface, which specifies a number of functions that a container runtime needs to implement in order to integrate with a kubelet. Just highlighting a couple here, for example, one of the more important ones is sync pod, which says, hey, here's a specification of a pod that I'm supposed to be running. Are we running it? We need to be running it. Or here's a specification of a pod that it's changed from the last time you run it, so just do whatever's necessary to align this with my current specification. This very much follows a declarative model, which is sort of one of the key aspects of Kubernetes. If you're not familiar with the API, basically, rather than telling Kubernetes, hey, start this, stop that, what you do is you provide it a desired state. Like, here's what I want to do. Here's how I want the world to look. And then Kubernetes is responsible for making the world look that way. And the same thing's happening within Kubernetes between the kubelet itself and then the runtime interface that runtimes need to implement. So in principle, it's very, very easy to add a new container runtime like Rocket or LXC or anything like that to Kubernetes. You just need to implement this simple Go interface. Well, it's actually a total mess. There's sort of hundreds and hundreds of lines of code in each of these things for the original Docker version. And there's a lot of assumptions scattered throughout the kubelet about Dockerisms. So this actually says 200, but I think it should be 300 commits. Took us about a year to really clean out a lot of this stuff and make it more kind of without going in the way overboard in terms of abstraction, but being able to just remove the Dockerisms and make it sort of a bare minimum of how we can integrate a different kind of container runtime with the kubelet. We're finally there, and so that's what rktnetes is. It's having Kubernetes using Rocket as this container runtime. So Rocket's going to do all these things like fetching images and executing pods and that sort of thing. Looking at this sort of architecturally, the current, without rktnetes, the way that Kubernetes is sort of running today by default, the kubelet just talks to the Docker daemon over HTTP API to do everything. So to fetch images, to start containers, stop containers, and then the Docker daemon is the parent for all the containers on the system. You'll notice there's nothing about pods here. What that means is that the kubelet has to maintain this state tracking between like, hey, I know what a pod is, and it consists of this container and that container. And if something changes, then it needs to kind of reconcile that state with Docker. This is actually a bit simplified because in newer versions of Docker, they've sort of split out their architecture. So now you have another daemon that starts the containers. So the kubelet sort of moving forward in terms of the Docker implementation is going to be kubelet talking to the Docker daemon, which talks to something called the containerd daemon, which is then responsible for starting up containers. And then the containerd daemon actually starts another new component called the containerd shim, which is responsible for starting up the individual containers itself. The nice thing about this is that then you can actually kill these things without affecting containers running on the system. The not nice part is now there's quite a bit of complexity, and we're still no closer to really knowing what a pod is over here. So in contrast, using Rocket as a kubelet's container runtime gives you some of those advantages of understanding pods natively, and then some other nice kind of things that come along with it, like a much better integration with systemd on systems that use systemd, which is, looking forward, realistically, that's going to be most Linux distributions. And again, you have this sort of self-contained model so that no Rocket pod affects any other Rocket pods running on the system. So looking a bit about what that looks like in more detail, there's a few different ways that Kubernetes talks to Rocket, because Rocket, again, exposes things in different ways, things that need different privileges, for example, and because it does less, ultimately, than Docker does. It doesn't have a long-running system that watches all containers on the system, so the way that we interact with it necessarily needs to be a bit different. So, in the RocketNetes world, what we have is, kubelet actually talks to systemd, running on your system, your init system, PID1, to start up Rocket pods running on the system. And then systemd is responsible for parenting those. At the same time, it talks to the Rocket API service to introspect information about pods running on the system. So to get information back out. And it does that over, talks to systemd over dbus using the native dbus bindings that we have in Go. And then kubelet talks to the Rocket API service, which is just a simple local daemon that understands the Rocket formats on disk over a gRP service. The nice thing about this is that this component or this component can die, or this component without affecting anything else. The only thing that's a single point of failure is systemd, but if your init system goes down, then your system's hosed anyway. So we think that's a pretty reasonable trade-off. So again, that's I sort of touched on some of the benefits of that. The other nice things you get is that all these sort of systemd commands like machinectl and journalctl all kind of just work with Rocket pods. So you can introspect and control pods on the system without needing any sort of special tooling there. But then, really looking at a bigger picture, as well as like we think Rocket's cool and we think Rocket should work with Kubernetes, a lot of this work that we've done has opened it up to be able to use Kubernetes, paves the way for other options within Kubernetes. So things like runc, we're starting to see a plan for integrating runc with Kubernetes. Things like Hyper, which is, there is an alternative kind of virtualization container system. And then looking a bit further abroad to Windows containers. So a lot of the work that we've done in the kubelet actually opens it up to being able to plug in different container runtimes and make Kubernetes, more broad. And really what's important about that is that this is forcing, Kubernetes to kind of keep them honest, getting rid of those assumptions about Docker, or those Dockerisms, and make sure that there's going to be a clean contract and understanding of what the kubelet's responsible for and what the container runtime is responsible for. And then, another way to look at it is like, it's cool, it allows runtimes to compete, right? So we can have sort of different, look at this different performance or this different feature that you get using different runtimes on Kubernetes. This is just a very stupid little comparison of one particular metric showing that Rocket's faster, but again, you shouldn't trust this, that you could find plenty of different metrics as well, showing that Docker's faster for some cases as well, so. So that's RocketNetes. Does it work? Yes. It was officially released in Kubernetes 1.3 a couple of months ago. It's not sort of 100% parity yet, but we're sort of tracking that for Kubernetes 1.5, and there's a feature tracking issue there, which I'd encourage you to follow along if you're interested. There's a getting started guide in the Kubernetes docs. Also, if you just go to roketnetes.io, and something that's happening, I think it's literally merged today, is support for RocketNetes in Minikube, which is a really, really easy way to get up and started running a Kubernetes cluster on your laptop in a VM. It abstracts away a lot of the magic around setting up the VM and stuff like that. So now you can set up a Kubernetes cluster running Rocket or running Docker very, very easily. Thanks.